In this lesson, we're going to learn about the last three types of chemical reactions that we're going to learn. So the first two are double replacement and single replacement. These three are, actually a lot more obvious and a little bit easier to deal with. So I just want you to just kind of recognize that. The first one we're going to do is something called combustion. Now, most of you probably have heard of combustion or combusting, something to do with fire and flames, and that's absolutely correct. We actually see quite a bit of these examples or use these real-life examples as examples of combustion. So the actual definition really comes down to the process of burning or a substance that reacts with oxygen gas and produces flame and heat. Now, again, the word combustion actually has a huge range of possible types of reactions, but we're really going to focus on a simple one that involves something called a hydrocarbon. Before I go any further, you can probably guess what kind of substances or what kind of elements are involved in a hydrocarbon. Hydro probably referring to hydrogen, and carbon referring to carbon. So those compounds that contain just hydrogens and carbons, or primarily composed of carbons and hydrogens, those will undergo combustion. A third type of element that might show up would be oxygen within the compound that we're talking about with a hydrocarbon, but again, typically it's going to be lots of C's and H's. When you have combustion reactions with hydrocarbons, you're always going to have two products. It'll always be carbon dioxide and water. But again, something that's not stated here in that line, but it's something that was mentioned earlier, is that you also need oxygen gas always as a reactant. Let's go and look at some examples of what type of problems you might see. The first one says a sample of methane gas, CH4, is burned to form carbon dioxide and water. Let's go and take a look at what kind of a problem this is, just so you have context for it. First of all, it does tell you that something is burned. Right there, big clue, combustion. Something else, they tell you that it's got carbon dioxide and water as products. Again, clues to help you know that it is a combustion reaction. And then one last thing is also just the fact they tell you that the formula is CH4. CH4 is got a bunch of C's, got a bunch of H's. It's called a hydrocarbon. So again, these are all clues to help you know that this is going to be a combustion reaction. So effectively, again, how we write this out comes down to what we just mentioned earlier. You know that the reactants are always going to be the hydrocarbon and whatever oxygen is around. And that's going to form two products always and forever, CO2 and H2O. If you go ahead and take a look at the states of matter, CH4, that's going to be a gas. It tells you it's gas, methane gas. O2, oxygen, that's a gas. CO2, I hope you know, is a gas. And H2O, your initial instinct may be to write L, right, liquid, because you know water is being a liquid. But then think about it, right? We're talking about burning something. That's a really hot environment. So what happens when water is in a really hot environment is that, in fact, it is a gas, not a liquid. So some of this context helps you figure out also to know that that's going to be a gas, not a liquid. Of course, to balance it, we go ahead and add the appropriate coefficients. Right now, we have to double the hydrogen. I'll do this in another color, make it more obvious. We have to double the hydrogens, or at least make sure this right side has a total of 4 hydrogens. Now there's a total of 4 oxygens on the right side. So left side, we're going to throw a 2 in front. Next example is, again, another problem that involves something about combustion. How do you know that? Once again, the word burn shows up. And then you also see that it's got a hydrocarbon right there, C5H12. Okay, so let's go ahead and set this one up. C5H12 is the hydrocarbon. Even though it's not specifically stated, the other reactant is oxygen. Once again, that's a hallmark of combustion. So it doesn't have to tell you that oxygen is going to be around. You just have to know that. And then again, because it is a combustion reaction, we have the same old CO2 and H2O that are going to be your products. After a while, you kind of get the hang of this because, the same general setup is present here. Pentane gas, again, is there. And then at this point, it becomes a matter of balancing. So on this one, let's go ahead and throw out the 6 for these. And then you've got to throw in 5 for that. And then when you balance it out for the oxygens at the very end, if you count it out, I'm sorry, let me go back and change these again. So that'll be 5 here. Oh, I did not hit it. Let's try that again. Okay, it's not working for me. Whatever the case, you see the coefficients here should be 5, should be 6, and then over here should be 8. All right, go ahead and take a look at the last one. This one is, again, a similar type of problem. A small beaker containing hexane is spilled and accidentally ignited. So go ahead and take a look at this one, set up the way we have in the past, or these other two examples, and then balance it out and write the states of matter. All right, that takes care of combustion. So we're going to look at the fourth type of reaction, which is called synthesis/combination. So these two words are interchangeable. They mean the same thing. It just depends on what you feel like using. Synthesis combination. The word synthesis is probably something you may have heard before, but the word synthesis is just a fancy way of saying combining, right? And that's why you also have combination reactions. So synthesis, in a lot of contexts, means you make something, you produce something. But this context, we're really talking about combining things where you have multiple substances A and B, and they make one. So multiple substances combining to form one substance. Couple types of synthesis reactions. One is that you usually have a metal combined with a nonmetal, and it makes an ionic compound. All right, that should be more or less obvious, right? Whenever you take a metal and combine it with some nonmetals, you expect to form an ionic compound because that's typically what ionic compounds are made of. There will also be other ones that exist, but those again are not going to be as there's not as much of a pattern, so you'll just be given the appropriate amount of information that you can just add the states of matter and whatnot to make it happen. So at the bottom here, an example: potassium metal and oxygen gas. These are combined. Well, again, potassium, right? That's a metal. That's one of the alkali metals. Oxygen, you should know now, is a nonmetal. So those are going to be combined. Now, that's not really a whole lot of information, but I think you have enough to work with because potassium, the symbol, oxygen is going to be O2, right? It's diatomic. It can't just be O. And then it's going to be combined to make a compound. Well, what exactly does that mean? Well, it's an ionic compound that involves K, which is a positive 1 charge. Oxide, right? Oxygen becomes an oxide, which is a negative 2 charge, and then you have K2O as a result, right? Positive 1, you need 2 of the potassiums. You have 1 O2, which is a negative 2. 1 O, which is a negative 2. So to make this a neutral compound, K2O. Remember, again, we're not just blindly copying stuff from the left side and smushing them together to make something on the right side. You have to be careful about how you put it together. Okay, a couple states of matter here. K, it's a metal, it's a solid. Oxygen, that's a gas. K2O, and this is the one that still takes a little bit of practice to recognize. It's an ionic compound. It's not really in any obvious water or watery environment. So that's going to be an ionic compound. That's going to be a solid. They're typically just solids that you can see around. And then, of course, got to finally balance everything. So let's go ahead and throw let's see if the red works this time, a 2 here, and that makes this a 4. Let's go and take a couple looks at some example problems here. We've got sodium metal and oxygen gas combined to form a gray powder. All right, so sodium metal, Na. I'll go ahead and throw a states of matter in there. It's a solid. Oxygen gas is going to be O2. I know that's G. That's going to form a gray powder. So let's try this out. Sodium and oxygen. Sodium is a +1 metal. Oxygen is a -2 anion, or non-metal. So again, Na2O. That's going to be a solid. Also, not only because it's an ionic compound, because it tells you there's going to be a gray powder. And so that helps you know that's going to be a solid there. And then at this point, we just go ahead and balance it. It's going to look actually very similar to what we saw before. It's going to be a 2 here and a quattro right there. This last one here, phosphorus powder combines with oxygen to form diphosphorus pentoxide crystals. Let's try this out. Phosphorus, they tell you the formula is P4, right? It's not just a P in this case, so we're going to throw that in there. It's combined with oxygen again, so surprise, O2. All right, that's going to form diphosphorus pentoxide. So that's going to be P2O5 crystals. All right, so it helps you know the state of matter for this one is not a gas, excuse me. It's a solid. This is a gas. This is a solid. And then you have to balance it. So to do that real quick, all right, you see that the right side definitely needs 2 of these. Makes it as a 4. That gives you a total of 10. That puts 5 right there. And so one of the great things about these is that, the combination reactions are pretty straightforward. One, if they tell you exactly what's there, they tell you exactly what's there, which is kind of nice. And then the only time you really have to kind of consider a little bit more beyond what's written is when they have these metal combined with nonmetals and they don't really say a whole lot else. For example, like you saw in either number 1 or in the previous slide, the last example there with potassium and oxygen. Same idea, right? If you have the metal nonmetal, just make it on a compound like you would any other day. All right, that takes care of synthesis. Let's move on to the last type, type 5. This is decomposition. Now, the word decomposition, I'm sure you've heard of before, and it sounds exactly like you might have an intuitive sense for. Decomposition is related to decompose, meaning we're taking something and breaking it down. So you can see here, it's the definition or the defined by a reaction where a single substance breaks down into multiple substances. So the general reaction, again, you have one thing being broken down to B and C, multiple things. All right, let's see how this works in practice. Granules of manganese 2 oxide is heated to decompose into each component element. All right, so let's see. Manganese 2 oxide, we'll start with that. Manganese is Mn2 oxide, so that's a positive 2 for manganese, negative 2 for oxygen, MnO. That's all you have to have. And it's heated to decompose into component elements, so that means it's going to be composed to Mn, right? It's just manganese. And then oxygen, which is O2. That's going to be a gas. This is going to be a solid. It says granules of it, so that's probably a solid. And then at this point you balance it. So to do that real quick, you have a 2, and then you have a 2 here. So again, this problem, again, just the way it looks, it should help you know that there's going to be a decomposition reaction because, again, you have one thing, MnO, and that forms two different things, Mn and O2. So this one right here is giving you some language to try out. This one, first one, a sample of white sodium bicarbonate powder is heated to decompose into sodium carbonate, carbon dioxide, and water vapor. All right, so let's try this out. Sodium bicarbonate powder, sodium bicarbonate, that's going to be Na, and that's going to be HCO3. That's going to decompose, right? So they tell you right there, there's no other reactant. There's just going to be that one substance. So you already know it's decomposition. And then you have sodium carbonate, which is Na2CO3, carbon dioxide, CO2, and water, H2O. Right, going back and adding states of matter, this is a solid. This is also a solid. Again, even though I don't really tell you exactly what it is, it's an ionic compound. It's not really dissolved in water. Even though there is water, you can see right here later on, that tells you it's water vapor. So water vapor isn't something you can really dissolve an ionic compound into. CO2, it's a gas, we know that. H2O now we know is also a gas because we're talking about decomposing it after heating it up. So that's going to be a gas as well. At this point, you just gotta have to balance it. This looks like it's quite a hefty, load to be able to balance it, but turns out, actually, it's a pretty quick one. Throw that in front here, and it's got it taken care of. All right, let's take a look at the last example. Potassium chloride and oxygen is generated when a strong flame is applied to potassium chlorate. All right, so let's see. In this case, I got potassium chlorate. Well, it looks like potassium chlorate is actually our reactant, right? So it's not just always presented in the order that you see here. And it says that the two products are potassium chloride, that's going to be KCl, and oxygen are produced. So let's go through it. Potassium chlorate, ionic compound, doesn't seem to have any obvious liquid involved, or at least any obvious water involved. It's going to be a solid. KCl, same thing, right? It's an ionic compound. And then, of course, you have the gas produced by oxygen. Okay, to balance it out, let's go ahead and see what happens here. Looks like we've got to double this. I'm going to have to triple that. And then I think you have to double that. So that about takes care of the three types. So once again, we have the three types: combustion, we have synthesis and or combination, and then finally we have decomposition. The very last slide I want to go over with you is just the states of matter business. I think for the most part, there's some amount of intuition and experience you have with certain substances to know what state of matter they are. These are going to be a little bit obvious, right? Because when it comes to maybe double replacement reactions, this is always in a watery environment, so you kind of know what to look for all the time. But when it comes to these other ones where it's not always in an obvious environment where you have to kind of make some guesses, I want to kind of give you a little bit of help. So a couple things. First of all, let's talk about the pure elements. If you ever see a pure element involved in a reaction, just know that pretty much all metals are solids, right? Every single metal is going to be a solid, except for the one mercury. Of course, that's got the symbol Hg. So you should kind of know that, again, from experience. It's not the first time you've seen this. Non-metals are a mixed bag, so that means that, it's kind of hard to know exactly which one's which. I hope that you at least have some basis of understanding that maybe hydrogen, oxygen, is a gas. Nitrogen probably is a gas. I hope you know that you're currently breathing air that is composed of 70% nitrogen gas. The other ones, I think are a little bit less obvious, so I think I'd give you some more clues. I'd hope you know carbon, right? Carbon is also a solid. And certain other things, probably won't be as obvious to you. So some language will help you figure out what the state of matter is. But again, I think the obvious ones are obvious, so I'd like for you to know those. Ionic compounds, I mentioned this a couple times already. If pure ionic compounds are involved, meaning they're not dissolved or they're not in any other weird state, they're considered solids, right? So you can expect that to be the case. All ionic compounds are pretty much solids at room temperature. And then if it's in a watery environment, you have to use the solubility rules. So that's why I kind of make that distinction, right? If it's in water or not. If it's in water, you can make another conclusion to see if it's soluble and then determining if it's going to be a solid or a aqueous substance. And then finally, any other substance that doesn't fit into these two, really you're just going to go ahead and give some clues or get some clues in the prompt. Okay, so that about wraps up. This is the last of the 5 types, and that'll do it.